Now I'm recording. All right. Oh, how fun was that, right, guys? Dead star. Nope, not for us. Not for us. Okay. At 2:40. I can't quite remember where we ended off. I think we started talking about just kind of how we can break down the effects. Oh, yeah. So, oh yeah, and I bungled it. I had the blocks and the treatments switched up, but it kind of makes more sense if we talk about, okay, the treatment effects and then the block effects, right? And so we figure out, and we use the little dot notation for just the overall row one effect or the overall row one mean, right? And that kind of thing. Okay, so yeah. Feeling like I didn't hit record, but I did. So we would find the averages, but then at the end of the day, we would find just the overall effects, right? And so what you're going to think about these as is kind of a layer of, okay, you've got your grand mean, and then you've got your treatment effects, and then you've got your block effects, and then finally you've got your residuals, right? And so we've got this kind of layering thing going on. And so our fitted values will be, or I'll say will consist of 3 layers. Our fitted value is going to be the overall mean plus the treatment effect plus the block effect. Sorry, I kind of ran out of room there, but right, so you think about it as, okay, you start with your grand mean, and then you add or subtract your treatment effect for each row, right? And then you add or subtract your block effect, right? And so we had our, where did we put them? Our treatments here, and our blocks here. Just in general. And we were able to find the effect and the effect. The effect being just the distance from the grand mean. And so here we would find 3 different treatment effects if we had 3 treatments. Treatment 1, 2, 3, oops, 2, 2. 1, 2, 3. Right. Treatment effect 1 would be, and I'll maybe erase that one, would be, is it the grand mean? No, it's the row mean, yeah. Row 1 mean minus the grand mean, right? Which we denoted as y1 dot bar minus y bar dot dot. Right. So the effect is the distance from the overall mean. And we've got it for both the rows and the columns. So the effect is the distance
from the overall mean. And each row would have the same row effect, right, or treatment effect, and each column would have the same effect. A row will have the same effect across all columns, and a column will have the same effect across all rows. Column will have the same effect across all rows. So what happens is, okay, you've got your grand mean, and then you add or subtract your treatment for each row, right, or your treatment effect for each row, and you add or subtract your block effect, right, for each column. And so each individual value, let's say you've got 3 blocks, right, each individual value would be different. Let me see if I might not have highlighted it. Let me see if I can find it. Oh yeah, we're gonna talk about Anscombe plots, but just in a second here. I got to the bottom of it. Oh yeah, so here, to find our fitted values, just for whatever we're talking about, right? We've got our blocks, which in this case is our subject, block 1, 2, 3, 4. And then we've got our treatments, right? So we have to be flexible on which is the rows and which is the columns. I can't remember what these are. Placebo, caffeine, and the realm of blah, blah, blah. Right, and so here, these are fitted values, but how we arrive there is, okay, we've got the grand mean, right, which is our overall mean of 34. That's the same for all of these values, right? But then we add the subject effects, which would be our block effects in this case, right? Each row has the same subject effect, right? And so what we do is from each of the first rows, we subtract 15. Second rows, we add 36 to 34. Right? And so that's how we take into account the subject effects or the block effects. And then we've got our treatment effects, which is going to be the same for each column in this case. Right? And so for the first cell, we subtract 12. So from 34, we subtract 15 and then we subtract 12. But then going across the row, right, we've got different treatment effects. And so I'll steal this little guy, this little graphic. Yes?
Where did they get 15?
Yeah, let me just pull it in here and paste it in. So the negative 15 would be from here, right? Let's say we've got 3 blocks in this general setup. The effect is going to be the distance from your column mean to your overall mean. and so that's kind of, I know it's where we ended off last day, so, but at the end of the day, we're just gonna use software for this kind of stuff anyway, so, but it is good to know where it comes from, right? And so, the distance, so in general, right, the effect is the distance from the overall mean, whether that's the distance of the column mean from the overall mean, or the row mean from the overall mean. That depends, right, which one you're talking about. Right. So this -15 says that for row 1, right, for block 1, that mean is 15 below 34. So here, the subject effects, these are our blocks in this case. And the drug effects, those are our treatment effects. Yeah, you're focusing on one of the blocks.
Yeah, I mean that if I do it that is
Mhm. No. Because if we think about it this way, right? So first, you're taking your overall average, right? That's where everyone starts from. Right? And then we're saying, okay, well, I know how each of these subjects in group number 1 are going to behave. Overall, on average, they're all going to go down 15 from 34. And so from 15, so down 15 from 34, because this is taking the block 1 mean minus the overall mean. Puts you at -34. And then the block 2 mean minus 34 puts you at 36. Right? So it must be 36 above 34. And so you can go through and do that for each of the blocks. And then you've got another layer, right? So now you've taken out, okay, now you've figured out how the blocks all change the means. And then you do the same thing for the treatments, where we're going to do this. Pardon?
19 minus 34, 50.
Good. In fact, I'll go in and I'll see if they've got it kind of close by. Oh, of course. Here. It's across the page or across the page break, but this is where the original data came from. So here, let's see if I can, how can I smush this together, you know, and still be kind of quick and breezy about it. Crop. There. Now I just have to piece this together here. Ish. All right, so now we've got these, they've put the blocks here. And then our treatments are in the rows, right? But it actually doesn't matter. So here, we've got our actual data. Block 1, treatment 1, we got an observation of 11. It doesn't really matter what happened here. If we take the average of 11, 26, and 20, right, we get 19. And then the overall average was 34, right? And so to get that negative 15 across each of the rows, right? Because now the effect for each of these is going to be negative 15, negative 15, negative 15. And so that's how we're going to find all these. And so let's see here. This is y bar dot dot, which is your overall mean. This is your y1 dot bar, which is the mean of row 1. And then the effect, this is going to be y1 dot bar minus y dot dot bar. And then same for the columns right down here, your effects. Just remember that we are talking about the fitted values, right? Your fitted values are your predicted values, right? And so here, that's one thing to keep in mind too, is that fitted values, they're predicted values. So they're not the actual data. They're what you would get from your y equals mx plus b, right? Let's take it back to basics, right? From your straight line, that's what you're getting with these fitted values. The difference here is what's missing is the residuals, right? Everything that's left over to give you your actual observed data. And so the residuals, is the observed, right? Your actual data minus your fitted values. Observed minus predicted. So now, what we've established is how to find those fitted values, right? Which is just going to be a layer of, okay, you've got your average, your overall average, your subject effect, your treatment effect, and then whatever's left over would be considered your residuals, right? There's nothing left. So then your residuals take your original data, right? Which is this 11, 26, 20, 56, 83, 71, right? And from each of these, so 11 minus 7 gives us our residual value for this cell, right? 26 minus 24 gives us the residual for the next cell, right? And so then we can just do the subtraction that way. They just map to each other. So the residual for cell number 1, for example, is going to be observed, which is 11, minus your fitted value, which is 7. 4. I think 4, right? My younger classes, they are always so weirded out when I don't do math in my head. Even stuff like that, I'm like, I don't know, and I don't really care. It doesn't matter. Pardon? Yeah, but not intellectually young. Yeah, intellectually, you're up here. Yeah. So, okay. If we have residuals, right, we know that we can do stuff with residuals, right? We can get a lot of information from our residuals. We do our residual analysis. We can do things like we can check the normality of our residuals, right? How are they behaving around 0? Do we have even scatter around 0, right? So we know those go-to things that we can check for our residuals, right? And so now that we're able to find these residuals, even though it's not as obvious, at least to me, to think about residuals in the ANOVA case as it is for regression, right? Regression, okay, we fit a line and then the distance from the line, those are residuals, right? Now we've got this kind of layering, and whatever's not captured by that layering, those are our residuals, but we can still treat them the same way. And so once we have residuals, we can assess the model fit using residual analysis. Oops. As before. Right. We've been doing it all along here, right? So in 6.4, we're going to be assessing the model. Oh shoot, where am I supposed to talk about that Anscombe plot that I told you? Okay, just hang tight. I'll read up on it some more. I want to say that the main problem was that they had actually squeezed 3 plots onto that same one. So one Anscombe plot is just a plot of one of the things. So either a treatment, probably a treatment, right? One of the treatments, and each point is a block. So, but you'll see that in the code. But how do I, now I've already introduced 6.4. Maybe remind me after, but I'll make a note after about those Anscombe plots. Okay, so now let's talk about assessing the model, right? So once we've landed on a model, there's a couple of things that you need to keep in mind, right? Do we need to do a transformation? Try it out. But once you've landed on a model that you think is pretty good, then we can assess the model. And again, we just use the residuals as always. And so we can assess the model fit using residual plots. Kind of our go-to ones are the residuals, residuals against the fitted values, right? That's our main one that we check, right? We're looking for random scatter around 0. We also have a QQ plot for normality. So we're checking, do we have a normal distribution? So once you have those residuals in hand, then we can still do that, right? You've got a lump of residuals. You can check them against the fitted values, which we just established how to find as well, right? And then you can check your QQ plot for normality. And then the one new plot that we have in this section is Tukey plot for non-additivity, right? And so what's kind of tricky is that it assumes that you have residuals already, right? And so remember the additive model that we have, right? Your overall mean plus your block effects plus your treatment effects plus your residuals, right? That's our additive model, right? We're just adding things on. And so now what we can do after we've picked a model that we think is pretty good, we can check Tukey's plot for additivity and just make sure that this additive model actually makes sense. To me, it's a little bit backwards just because, okay, we've picked a model, we think it's pretty good. Now we're going to make sure that there's not something better that we could be doing. Right? So we're still kind of checking our model here. But the third thing that we can do, and I'll put a star here, this is new, a new plot for us, is the Tukey plot for additivity. Sorry, non-additivity. I skipped a very important prefix, non-additivity. Although, I guess it could just as easily be additivity, doesn't matter. You're checking to see if the model, so here, I'm dealing with a page break here, so I'll keep it nice and shallow. But this checks to see if we need a change of scale. Change of scale, right, which is essentially a transformation. Okay. So what are the components for the Tukey plot for non-additivity? First thing you're going to do is you have to fit the model, right? Pick your best model, and now we're assessing it. I don't remember using this necessarily. I would suspect that you would use it as an argument that your model is the best that it can be, right? So it's more of okay, here, there's nothing going on here, and so I'm okay to use this additive model, right? It's not about checking to see really what we should be doing at this point, but if we find something, then of course we have to go back and change it, right? So, but I would probably just use it as an argument that, hey, my model is as good as it can be, right? So first thing, you have to fit the model, and then we have to compute what they call a comparison value. So compute comparison values. And the comparison value is going to be the row effect, right? Because each of the row has an effect, right? Times the column effect, sneak that in there. So each of the cells, right, is going to have a row effect and a column effect. So you multiply those, and then you divide it by the grand mean. Right. So going back to the numbers that we have, because it's easier to think about, right? Our comparison value would be, you can look at this table here, right? Our comparison value would be our row effect, -15, times our column effect, -12, divided by our grand mean, 34. That's our comparison value for this cell. Right? For this next cell, it's going to be -15 times 5 divided by 34. For the next cell, it's -15 times 7 divided by 34. right? So each of them get different comparison values. So you've got these comparison values. So now, bless you, what you're gonna do, the third thing you're gonna do is you're gonna plot the residuals against these comparison values. Plot the residuals, and I'll use that tilde. Is that okay? You guys are all plotting in R anyways, so plot the residuals against the comparison values. If the points follow a line, right, then an additive model is going to be appropriate, right? It might be the one that we have, it might just be some other model, right? But some sort of additive model exists that we can use. Let's see here. So if the points follow a line, we can use some additive model. Now, again, we're going to use the slope of that line to figure out what the transformation should be. And so, to figure out an appropriate transformation, we use the slope of the line again, and I'm issuing an apology / errata, because I think I said, I can't remember, in chapter 5, in the general methods document that I posted, I had the right value, but in our notes, and no wonder I was so confused, if the slope is 2, then we use 1 over y. I'll write it down. But here, whereas I think I said if the slope is -1, then we use 1 over y, and it didn't make sense. And I said, just don't think too much about it. Don't worry, you were right. So the power is, it's just that my eyes jumped over a little bit. 1 minus the slope. But here I am, a formal apology / errata. So, so the power is going to be 1 minus the slope, and a slope of 0 means take the logs, or take the log. I'll even do it in red. Correction. In chapter 5, a slope equal to 2 means that the power is 1 minus 2, which is -1, so the transformation is 1 over y. Whereas I think I had said not if the slope is -1, then the transformation is 1 over y. I'm pretty sure I said if the slope is -1, then the transformation is 1 over y. But I meant if the power is -1, then the transformation is 1/y. So just make sure that you go back and fix that. But like I said, in that general document, I had it all figured out. But okay. Okay. Phew. It's worried out. Forget that.
When you need,
Here.
it says, if the points follow a line, you mean fitted line.
Yeah. So if the residuals versus the comparison values, if they follow some sort of a line, then we can use an additive model.
So we fit a line on the residuals versus.
That's right. Yeah. If there's some sort of curvature, for example, then there's something that's missing that won't be captured by an additive model.
Do you do eyeball or do you
Yeah.
really fit that?
I would eyeball it first. You can fit a line to see how things fit around that line, right? Because I mean, that doesn't take very much at all, right? And so I would probably just go ahead and fit the line and see what the slope is. But I would also want to make sure that I don't have this non-linear relationship, right? And so if we've got, so if the points follow a line, right, then we can use some additive model. If we have a non-linear relationship, so versus a non-linear relationship, right, then it's not additive. Meaning we probably need to introduce some sort of interaction term, which we'll get into next day, or something like that. Yeah.
Slope is 0, it's a vertical line. That means all the residuals in the.
But if the slope is 0, we've got that weird special case where that means just take the logs.
We use generally log to simplify the equation.
Yeah.
So we are simplifying multiple equations divided.
Say that again.
We use log to simplify the equation, right? So
Yeah.
we have a into b, we use log to a plus b. So we are taking multiple into addition. If we don't have any slope, it says it's a vertical line. But if you are transforming it by using log,
Well, a no slope versus a slope of 0. Right, so if you have a slope of 0, you've got this vertical, right? Or sorry, horizontal relationship. Whereas no slope, then it's completely straight up and down. Then something really weird is going on, right? Because then it doesn't matter. All your comparison values would be the same. Right? But that's not gonna happen unless all your treatment effects and all your column effects were the same. And then there's nothing to capture. So, yeah, the difference between no slope and 0 slope. 0 slope is the logs. Not that, in my mind, it still doesn't really, click why it would be logs, but that's just our default, right? So if there's nothing going on here, then we can use logs, and it'll probably help. Okay. Okay. Any other questions about that? So that's that new plot that we can use to check if we have an additive model. Section 6.5 is on using the model. So what can we do here? What conclusions can we draw, right? And so once we've introduced a block term, we've actually got two hypotheses that we're testing, right? And you guys caught on to that pretty quickly, because as soon as I showed you that the ANOVA output, you said, hey, there's two p-values there, right? One's for the block effects and one's for the treatment effects. And so now that we have a model, with treatment and block effects, we will be testing two hypotheses. The first one is for the treatment, which in general is going to be alpha 1 equals alpha 2 equals alpha 3 all the way up to equal to 0. Remember, you can use alpha or tau for the treatment. Or tau 1, tau 2. We used alpha for the one-way ANOVA. And then I guess I'm being inconsistent because I said, okay, let's use tau for treatment when we've got blocks and we want to differentiate. But what we're saying here, right, this null hypothesis is that there's no effect due to the treatment, right? So there's no treatment effect. So there's no effect due to the treatment. Right, or no significant treatment effect. So that's what the p-value is for the treatment, right? Whether there's some sort of significant treatment effect, right? Were we able to capture something between the different treatments that we applied? And then, oh, I guess it's also in light blue, right? Then we can test on our blocks. The null hypothesis is that beta 1 equals beta 2 equals beta 3, all the way across equal to 0. Notice that we're checking all of these against 0, right? There's nothing going on in the treatments. There's nothing going on in the blocks. So what's this saying? This is saying that there's no effect due to blocks. No effect due to the blocks, or the blocking if you want. Or if you prefer, there's no significant blocking effect. No significant blocking effect. Oh. So these are the hypotheses that we're testing. And of course, we're hoping that we get some sort of significance going on here. One thing that can happen, right, is if you should have blocks, but you don't have blocks, right, then you get an insignificant result for your treatment, right? If you're only looking at your treatment effect, right, so a one-way ANOVA, let's chapter 5, right, one-way ANOVA versus one with a blocking effect, right? In a one-way ANOVA, what's possible is that we're not able to capture the treatment effects because the residuals are so blown out of proportion, because we're not able to capture that blocking that exists, but we haven't pulled it out, right? And so sometimes what happens is, if we're looking at a one-way ANOVA that's not significant, but we think that it should be, right, then there's probably blocks missing, right? And then when we introduce those blocks, then what can happen is that everything becomes significant, right? The blocking effect then is significant, of course, because it made a difference, but also we're able to see those treatment differences. And so how do I summarize that here? It is possible to have a one-way ANOVA that is not significant, because there are underlying blocks that haven't been taken into account. So because there are underlying blocks that haven't been taken into account. Once we take the blocks into our model, right, once we add these blocks into our model, then again, it's possible, it's not always the case, right, but then it's possible that we get a significant treatment effect as well. Right? And so if we add in a treatment, or sorry, a blocking effect to our model, it is possible. So again, this is kind of a situation, but it does happen, right? Where, like we were saying earlier with that lab that you're working on, right? It's possible that the reason that things aren't behaving exactly how you expect them to is because maybe there's some blocking that's missing, right? There's something that hasn't been captured. So if we add in a blocking effect to our model, it's possible that we will find significant treatment effects. Significant treatment effects that were basically just being lost because we weren't capturing that blocking.
The way I understood it is that if you cannot conclude anything using your one-way ANOVA,
Mm-hmm.
then you might want to think of going to blocking. Right?
Yeah.
But if you already have a significant effect on the treatment,
Yeah.
you don't need to cheat.
No, you might get more information if you block, but if you have a significant treatment effect, you did it, right? Then you were able to capture that, and you didn't need to extract all that blocking kind of noise. But usually the case is that we just don't have data to make those blocks, right? And so then we're hooped, right? And I don't remember what the slugs data looks like. Do you have variables in there that you could? No, right? It's just your, yeah. So in that case, right, that's one of those examples where, okay, well, you think there might be some blocking that you should be doing, but you can't because you don't have anything to block on, right? And so that's just something that you can just say, and hey, here's a limitation that I'm facing, and you just say that, and then I would try blocking if I could, type of deal, and then you move on. Right? So yeah, and I think it's set up that way for a reason, right? So you don't go out of control and say, oh, I heard about blocking, I'm just gonna do that, right? So here, right, we're limited because we've only got our treatment and our response. That's it. Right? Of course, real life, we would have more information and we could try it, but yeah, so that's good, good.
So I have 10 explanatory variables,
Mm-hmm.
which are categorical.
Okay.
I have grouped them into one and tried to do one way.
Okay.
And or I've grouped them into two.
Mm-hmm.
Two way.
Okay.
So if I get good results in the first thing over two-way,
Uh-huh.
so why don't we just use one-way always?
You're not gonna get a better model with one way than a two-way. It's possible that you get the same model, but it's kind of like I'll resort to regression just because it's easier to think about, right? If we so you've got your simple linear regression, right? Adding another predictor might get you a better fit. It's not going to give you a worse fit, right? But it also might not do anything, right? It might not add anything. So the same thing is going to happen with the blocking, right? So we might be able to see a treatment effect already. Adding the blocks isn't going to hurt, but it might not help, right? So then you would argue, okay, well, I can use the simpler model and have the same results, right? And so that's when you would use that one-way ANOVA, because you can, right? Because we're always trying to shrink down our models so that we get the smallest, the best, smallest model that we can. Right? And so, yeah, so if you're finding that, okay, my treatment isn't actually doing anything, right, then you can pull it out, make sure that you get kind of the same results, and then use the simpler model. Okay. Oh, before I forget, well, I guess I can show you guys later for the lab. I posted a new lab, I'm pretty sure, just before I took off, so I don't know. Who knows what happened last week? It's all a blur. Okay. Just as before, right, we can make confidence intervals, and we can do effect sizes, right? And so, and all those things behave the same way, so nothing's really changed there. And so, as in the one-way ANOVA case, we can construct, oops. we can construct confidence intervals. Oh man. Construct confidence intervals. And calculate effect sizes. But now we can do it for both the treatments and the blocks if we wanted to. Usually our main focus is still the treatments, right? For the treatments, and the blocks. Usually, we're more concerned with the treatment, right? We're more concerned with the treatment than the block, right? It might be nice to say, okay, well, this block had this effect size, that type of thing, but usually we're more concerned about talking about, okay, I'm 95% confident that the treatment for this effect, or the treatment effect for this group is, you know, this much. So those calculations stay the same, so we're not gonna. The effect size for one-way ANOVA is just how large, is it from the overall mean, I think? So the treatment effect, how large is it in comparison to the spread of the other effects, right? Same case with the paired. But you can do it for individuals too, right? But usually we talk about pairs, right? Yeah. And I'm pretty sure in that document I posted, I showed you how to do both, right? The individual ones, but also the pairwise, which is easier to talk about, right? This compared to this. The effect size of this compared to this was large, right? For individuals, it's I find harder to talk about, right? Because it's the comparison to the overall data. Good. Okay. I think that's, oh, I knew it. I knew I had something that I wanted to talk about. Where are those dang Anscombe plots? I've made too many notes in this thing. That's the problem. Even when I tell it to only show me the highlighted things. Okay. The one that we were looking at before, the Anscombe plot, this guy here, when I dove into the code that they used to make this thing, you're absolutely right. It is 3 Anscombe plots on the same graph, right? Which I guess we can do, that's fine. It's confusing though, because they didn't, you know, really introduce these things. But an Anscombe plot is just gonna be, look like something like this guy on the left-hand side. You can do it for the fitted values as well. But here, right, each point is going to be a block. And then, so we're talking about, these were twins who live in a rural community versus an urban community. And it's something about how their lungs clear, I don't know, bad air or something like that. Anyways, So each block is a pair of twins, right? So in this case, it was the simplest scenario, right? Because you've got one twin in rural and one twin in urban. And so now your treatment is basically where they live. Right? And so each point is going to be a block. But you'll get some code, not from me, miraculously, and you can kind of have a look and see what's going on in those Anscombe plots, because I'm all out of time. Anyways, any questions? No. So I posted the next lab, but I know you've got some time to work on lab 5. I can't remember the lab numbers anymore. Lab 4, lab 5, or lab 16. Okay, cool.